In pursuit of transferring technical knowledge and just to gear up for the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 19. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with analyzing power transformer operating limitations. Various factors that influence operational objectives of the power transformers. Transformers, while in operation, tend to generate certain amount of heat, which is mainly due to the reason for conversion of energy inside the transformer. Intended heat that would have to vary with the quantum of load which is applied to the transformer. For safe operation, the loading of oil immersed power transformer should never be run beyond their respective thermal ratings, which are to be determined by analyzing certain variables and consequential factors. Consequential factors are as follows, which can establish continuous emergency and short-term emergency transformer thermal ratings. Again, I repeat, consequential factors are as follows, which can establish continuous emergency and short-term emergency transformer thermal ratings. The amount of heat as produced in the copper windings, that is load losses. Number two, the amount of heat as produced in the iron core, that is no load losses. Number three, occurrence of transformer overloading during contingency conditions. So, number one, load current is responsible for producing heat. It is understood that the load loss is quite relevant with the load current flows through the transformer windings and produces resistive losses, that is copper loss, as proportional to load current. Load current has to exhibit twofold effect on transformer while in operation. One, with the increase of load current, the amount of heat as produced would have become much more significant. See the figure 86. There will be a voltage drop across the output windings as corresponds to the load current with winding resistance and reactance. So, an internal voltage drop would have to occur in the output windings of the transformer by an amount depending on the effective impedance and the load current as being supplied. Due to have the winding resistance and leakage reactance expressed as a percentage of the rated voltage, so the percentage impedance of a transformer is the percentage change in the output voltage from no load to full load. It is also to be mentioned that the load power factor is always be a determining factor for the output side voltage. Therefore, this percentage change in the output voltage, that is voltage regulation, would have been influenced by the load power factor also. See the diagram. Relationship between load current and heat produced in transformer windings. Iron loss as related to voltage and frequency. Iron loss, that is eddy current loss and hysteresis loss, are almost independent of load current but significantly depends on supply voltage and frequency. V by F is directly proportional to phi, where phi is the amount of magnetic flux in core laminations, and for higher flux than its rated capacity leads to increased eddy current and hysteresis losses. Flux density or flux, if it is being constant within the core laminations for a given voltage and frequency, then eddy current loss and hysteresis loss also remain constant at any load. So any variation of voltage and frequency would have to affect the iron losses, that is hysteresis and eddy current losses in a transformer. If transformer voltage and frequency changes in the same proportion, then core flux density will remain unchanged. Hence, the no load current will also remain unaffected. In designing for core construction and selection of winding insulations, it is quite convenient that the operating voltage and frequency must have to be kept in consideration within rated values. Keeping at rated frequency, if any transformer operates at higher than rated voltage, then core flux would have to increase. Similarly, keeping at rated voltage, if any transformer operates at lower than rated frequency, then also core flux would have to increase. An extra amount of heat is produced in both the cases as due to the effects of hysteresis and eddy current losses. However, if the frequency is increased with constant supply voltage, then hysteresis loss would have been reduced and eddy current loss is being unaffected. Understanding with the thermal aspects of the transformer, various system elements are then being designed to incorporate for effective heat transfer mechanism by applying some form of coolant and cooling system. The temperature class of winding insulation would have been selected as per the respective relationship between the load loss, no load loss, and corresponding heat produced in the transformer core and winding, including connecting leads. For larger capacity dry type transformers, obviously of air cooled, should have their windings be insulated, usually with class F insulation of temperature limit 155 degrees centigrade. And to have a better cooling provisions, some air ducts are therefore to be designed for allowing air to circulate through the windings and over the core surface of the transformer. Dry type transformers are often used for purpose of low voltage and medium voltage, that is 1000 volt to 35 kV applications. However, performance of dry type transformers under overload is rather limited, as because this type of transformers might not be ideal when transformers need to be overloaded to mitigate contingency conditions. The sharp rise of temperature above the standardized temperature range would have been the main issue in order to perform over the rated load. To counter this temperature issue, additional cooling fans have to be installed with the purpose of accelerating the dissipation of heat through forced convection. No load and load losses both are therefore be responsible for thermal loading of a transformer, and if it is not controlled in a timely manner, then there will be every possibility of damaging the dielectric properties of the insulations. When transformers need to be overloaded to mitigate contingency conditions, it is better to follow some specific operational guidelines as per recommended practices of the Institute of Electrical and Electronics Engineers, INC, IEEE Transformer Committee. Note: C57 9.96 in the year 1989, IEEE Guide for Loading Dye-type Distribution and Power Transformers, which includes recommendations for ventilated, non-ventilated, and sealed dry-type transformers having impregnated insulation system. For conversion of medium high, that is 35 kV to 230 kV, and extra high voltage, that is 230 kV and above, their use of oil-filled transformers are typically more efficient than dry-type transformers. Using the IEEE guide for loading of oil immersed power transformer C57.91 in the year 1995, engineers are able to establish continuous, emergency, and short-term emergency transformer ratings and can use these ratings until the contingency conditions are mitigated. However, once the transformer has crossed over the short-term emergency ratings, the transformer might have been touched the critical temperatures and could possibly sustain damage. The longevity of the transformer can be comprehended as the rise of temperature due to thermal process is thereby controlled by the provision of cooling system that keeps the transformer in a thermal equilibrium. The oil-filled power transformers are composed of mineral-based oil with cellulose paper as insulation installed between windings of the same phase, windings to ground, and windings from different phases. Performance on thermal perspective and designing considerations. Heat generated due to no load and load losses is the main source of temperature rise in the transformer. Ferromagnetic core windings, and corresponding insulations all have their own specific thermal capabilities. If somehow the rise of temperature and the thermal process would have been forced to exceed the extreme limit of their thermal capability, then it is quite evident to have a chance of premature failure of the transformer. The generation of heat as produced by the core will have to depend on the grade of ferromagnetic material and its flux density. As the hottest zone of the core is rather difficult to locate and also impossible to access, so natural circulation of oil is usually be the core cooling process. To avoid overheating of winding insulation, it is better to specify that the maximum temperature rise for the surface of the core should not exceed the maximum temperature permitted for windings. However, the cooling process of the transformer windings by calculating the effect of aging insulation and its exposure to high temperatures must have to represent the most important thermal aspect of the transformer design. The thermal energy produced by the windings is transferred to the winding insulation and consequently to the oil and transformer walls. Whatever may be the temperature rise, copper itself always be able to withstand its own mechanical strength, and usually the insulating oil would not start to degrade up to a temperature of 140 degrees centigrade. But degradation of paper insulation, cellulose paper insulation, that is kraft paper, would have to be started beyond 80 degrees centigrade temperature, and significant deterioration would have been exhibited while temperature rises above 90 degrees centigrade. Considering the ambient temperature as a base value, the design temperature limits for transformers would have to express as the rise of temperature above the prescribed ambient temperatures. Now, principal sources which are mainly responsible for heat generation within the transformer: one, coal loss; number two, copper loss in windings, I square R loss; number three, stray loss in windings; number four, stray loss due to leakage and high current field; number five, leading to a high contact resistance as due to have loose electrical connections inside the transformer. Transformer winding and oil temperature rise would have to depend on: one, in IEC 60076 part 2, that is second edition, 1993, maximum ambient temperature of 40 degrees centigrade is specified with a limit on top oil temperature rise of 60 degrees centigrade. Number two, as corresponds to maximum ambient temperature of 50 degrees centigrade, then top oil temperature rise limit is therefore be reduced to 50 degrees centigrade. Number three is the most important one. As the air density at altitude of more than 1000 meters above the sea level has become drastically reduced, so the purpose of convective heat transfer criteria is therefore be badly affected, and special corrective action should have to be designed as per requirement. Number four, specified standards so as to be followed during selection of designing parameters. Number five, specific loading characteristics. And number six, cooling system as provided. For power transformer, while in operation, the power losses as incurred by the windings, core, and iron structures are then converted to heat, resulting a rise of temperature inside the transformer, which ultimately dissipated through a complicated path. From the perspective of optimal design, the heat transfer objective has to be implemented after analyzing the thermal performance of the coolants as used. In three-phase oil immersed power transformer, where the oil provides a medium for both cooling and insulation, heat is taken away by the transformer oil from the core and windings and dissipated that heat ultimately through cooling fins, tank surface, or radiator to ambient. So far the core is concerned, heat transfer to oil is direct. Again, I repeat, so far the core is concerned, heat transfer to oil is direct. But in case of winding, as the conductors are well insulated, so heat transfer from copper to the coolant must be through the small thickness of insulating material as provided. Mode of heat transfer in oil field transformer. One, conduction of heat transfer mechanism in the active parts from the interior hotspot to regions exposed to oil. Number two, convective heat transfer from surfaces of the active parts to oil. Number 3, convective heat transfer from oil to internal surface of the transformer tank. Number 4, conduction of heat from internal surface of the tank to its outside surface. Number 5, heat transfer from tank surface to ambient by means of both through natural convection and radiation. Note, active parts which are mentioned in number 1, core, HV winding and LV winding. In oil-cooled transformers, number 2, convection plays the most important role as compared to conduction, which refers to be the least important. As per convection of transfer law, heat transfer law, transferring thermal energy from one medium to another for the purpose of cooling. See the diagram. This is the radiator banks. Transfer of winding heat, transfer of core heat, transfer of winding heat, oil flow. Change of oil volume with temperature provides the essential convective or thermosiphon cooling. In oil-filled transformer, the energized core and current carrying components are totally immersed in oil, so maintaining required oil level is extremely important. Volume of the oil has to change with temperature and pressure, and during operation of a transformer, such phenomenon would have to provide twofold effects. One, the most essential convective or thermosiphon cooling system is therefore to be effectively established when oil volume starts changing with rise of temperature. Number 2, the amount of vibrations as transferred from core to tank through oil would have become much more significant while the oil volume starts changing with rise of pressure. In energized condition, as the oil density has to reduce with rise of temperature, so in accordance with the principle of convection, the heated oil would have to flow in the upward direction and then starts entering in the top valve, top half opening of radiator tubes, and the vacant oil space in the tank is thus to be filled up by the colder oil through bottom opening of the radiator tubes. Thus, continuous oil circulation process would have been established due to natural convection and heat dissipation process to atmosphere that has to occur due to natural conduction. If the oil level falls below the level of the radiator inlet, flow through the radiator will cease and the transformer will overheat. If the oil level falls below the level of the radiator inlet, flow through the radiator will cease, and the transformer will overheat. If oil level is too high, then there have been the possibility of over pressurization inside the transformer tank, and it has become much more alarming when the oil starts expanding as corresponds to rise of temperature. The problem of contraction and expansion of oil would have been countered by two types of application: A, air breathing type, and B, hermetically sealed type. This will be discussed later on. Let's stop here. Further to be continued at later stage. Thank you. Thank you for patient hearing or listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.